What's this pen? Blue. Alright then, what we're going to do this time is we're going to do proof by induction. This is where we can use our tools of writing with our set notation to actually prove things. You see, in mathematics you need to prove things. You can't just say this is mathematically correct without being able to prove it. One of the best way of doing this is this proof by exhaustion. Now it's called exhaustion because it's meant to be exhausting, so let's just get straight on it before we get tired. I feel like I'm out of breath already. Anyway. So there are things that you can do in maths where if someone gives you a statement like 11 is a prime number, you can check that by checking all situations which would make it not a prime number. So the definition of a prime is that it's only divisible by itself and 1. So to check if it's a prime number, you would just divide it by 2, 3, 4, 5, and then eventually you would go, well, it's not divisible by any of these numbers. Now to actually put this into some form of steps, we can, well, let me show you. So I've written this down into 2 little steps. The first step, let's get a red pen ready for this. Break up your statement into multiple situations. So like 11, we're breaking up into the situation where you're dividing by numbers smaller than it. That would mean you can check if it's a prime number. Then after you've got it into these multiple situations, you check every single one. That's why it's exhausting, because you are going to get exhausted. Hopefully, maybe. Let's try an example. So I said about 11 being a prime number. Too easy. Let's go in with 29, yeah? So I'll get this question on the board in black, but to make this easier, we're going to use a little thing called prime factors. So think about it, then I'm going to explain that. I've said sure 29 is a prime here, but it's the exact same thing as saying prove 29 is a prime. Now I said about dividing by all numbers less than 29, but actually we can just skip to dividing by prime numbers, because there's a thing called prime factors where every number can be expressed as a multiple of prime factors. Now you can, let me show you quite quickly, right? Say a different number, 24, not a prime. So we can divide it into its 2 factors. Let's just say 12 and 2. 2 is a prime, we're going to stop there. 12 can go 3 and 4. 4 can go to 2 and 2. Then what this means is that 24 can be written as a multiple of these prime factors. 2 times 2 times 2 times 3. This is prime factors. So all we need to do is divide by numbers less than 29 that are also prime. So let's just get busy with that. But no, wait. Just because we can, let's actually write and define what a prime is using our set notation. Now this might take a moment, so this here is how we can define a prime using set notation. What we've said is that a prime number, p, is any number which p is a member of the naturals not including 1. This is set difference notation. We're saying it's naturals but not including this little set here, which is 1, which is saying 1 is not a prime. Where p, so I've said that this p is divisible by p and 1 only. So it can only be divisible by itself and 1. When I say I mean divisible, it's you're going to get an integer by dividing through that. This is kind of like a bodged way of saying this is what a prime is. Just a nice quick and easy reference. Now this looks like it says penis a little bit, which I'm going to not include in the video. Anyway, now we know what a prime is, we're going to divide by numbers less than 29, but prime numbers. So let's just get moving. 29 divided by 2 equals 14.5. That is not a whole number. 29 divided by 3 is 9.6. That's not a whole number. 29 divided by 5, 8.5. That is not a whole number, and yeah, I've realised it's actually 5.8. Now if I was to write the rest down, I'm not remembering them, I've got them written down here. What we'll find is I've gone up to 13 because actually if we went past 13, if we went to the next prime which is 17, I'll do it here, 29 divided by 17, that equals, the old class whiz, 1.70 something something, which is not an integer. Here it's less than 2, so any numbers which are greater than half, we don't actually have to test to divide by them because we've kind of already done it. So this one, not needed. So what we've done here is we've already proved that 29 is a prime because it's not divisible by any primes which are less than half of itself. So we've already proved that 29 is a prime, but we have to finish our little proof by writing this as a sentence. So, how do we write this as a sentence? All you have to do is say, therefore, 3 little dots, 29 is a prime as this little square means end of proof. Bam, we're done. 29 is a prime as it cannot be expressed as a multiple of primes. We've used our little tool here, this one. This is our prime factors. Bam, done. Now sometimes these proof by exhaustion questions that you might get are actually really quite tricky and they involve a lot of algebra. It dips its toes into something called proof by deduction. So let's have a question which is kind of using algebra. This is our question. Prove that when n squared is divided by 5, the remainder is 0, 1 or 4 for all n in the integers, the zintegers. So no matter what number we put in there, we divide it by 5, we're going to get a remainder of 0, so it's divisible, 1 or 4. Now step 1 is to break up the statement into multiple situations. Our multiple situations here, it kind of looks like it's all the integers, every single one. To do this proof by exhaustion then, are we going to have to check and try every single integer? That's going to take a long time because we'd put 1 in, 1 squared is 1, divide that by 5, then you get a remainder of 1. Bam, it's true. But that's going to take a long time, an infinite amount of time because there's an infinite number of integers. So we have to think of a way that we can break our integers up into smaller bite-sized chunks. Now a nice way of doing this is using this little trick. Now I'm going to say, right, 5k. We're just going to start with this, 5k. This is 5 times any integer. Let k be any integer. Then 5k is any number which is a multiple of 5. Now, that's alright. What about that? This is any number which is a multiple of 5, but 1 more than it. What we've got here, 5k plus 1, 5k plus 2, 5k plus 3, and 5k plus 4. This, depending on what your integer is, spans all of the integers. For example, if we had k equals 1, 5, 6, 7, 8, 9. K equals 2, 10, 11, 12, 13, 14. K equals 0, 0, 1, 2, 3, 4. We don't have 5k plus 5 because that's just 5k but for a different k. So we've actually broken up every single integer, an infinite number of integers, into 5 situations. Isn't that good? Then all we have to do is put each of these in n squared and see what we get out the other side. So if we start with 5k, this implies n squared equals 25k squared, which equals, well, let's just do implies. We could clearly take a factor of 5 out of there because it's 5 times 5 is 25. So then we get a remainder of 0. Bing! Nice one. Let's try this one. 5k plus 1 squared. So this is going to be all of that squared. 25k squared plus 10k plus 1. Now this one implies our remainder equals, it's that 1 on the end. 1. We'll do it again for here. This one implies n squared equals 5k plus 2. Now we've got a remainder of 4 because we've got a plus 4 on the end. The next one we're going to have exactly the same situation but a plus 9 on the end. So n squared equals that squared, 25k squared plus 30k plus 9. Now the 9, when you divide that by, you've got 9 in the end, but when you divide that by 5 you actually get 4 left over. So now our remainder is 4 again. And with 5k plus 4 we're just going to do the algebra. R equals 1. Bam! So this one has shown that, this one has shown this. Whew, exhausted. We are done. However, as with all proofs, we need to finish our little proof by saying something like, oh, where are we on the screen? Are we on the screen here? Yeah. Therefore, n squared over 5 gives r equals 0, 1 or 4 for all n in the integers. I would expect someone, if they were doing this like properly written on paper, to not squeeze on the final conclusion there, like the final statement. Little box. You have ample room on your like question papers or in paper that you're just writing on. So it's always good to lay out your work when proving things really methodically, really logically, and then you pick up all those marks. Now, proof by exhaustion can get quite hard because you have to use your big brain to figure out how to split up situations, but essentially this, or odds and evens, and each little step that you do is actually kind of a proof by deduction, so you're doing like multiple ones of it. It's quite nice actually, but it's not really used too much in mathematics because sometimes you can't break it up into multiple steps, and that's step 1. If you don't break it up into multiple situations, then it's going to take you a long time, and this is why the computing age makes good use of this, because you can just set your computer to do things over and over again. And that's why people have used this to solve games. And now I know, like, how do you solve a game? Now think of something really simple like noughts and crosses. Really simple. You put your x here, you put your naught here, and so forth. If we work on the assumption that everyone plays their perfect game, like you don't do any daft mistakes, you can do proof by exhaustion to work out all the possible moves to see who's going to win based upon the first move, the very first move. So like, we could play tic-tac-toe, noughts and crosses, right here. We might get up to this part of the game. X to play next. This one, we know who's going to win because playing your perfect move, if you were It's 0 to plane x. 0 to plane x. If you're a 0, you'd be like, oh man, I need to block x. I'm going there. X, you're obviously going to go there. You wouldn't go there because you're playing a perfect game. You go there, you win. However, computationally, it's been proved from just the first move. Now, noughts and crosses isn't a particularly exciting game, but Connect 4 is. And people have solved Connect 4. I like that game. That's a shame. Anyway, this was proof by exhaustion. Good stuff. Just before I go, the main points here. That's really good. Your steps, golden. But this bit is worth remembering. These kind of ones are where you'd get like 4-mark questions where you're doing quite a nice, conceptually difficult, splitting up into multiple situations. If you remember that and these 2 steps, then you're golden.